Swayam Prabha. Digital India. Educated India.
Good morning, everyone. I know it's a very intensive course, right? And 3 hours a day is not, especially this course, wave energy, as we learned, is really, really multidisciplinary, right? We need to know a lot of things. So far, we learned vibration, right? We also learned the wave dynamics. Basically, the potential flow, right? And we get the concept of wave energy, how much in the water, and how the particle move, right? Deep water and shallow water will be different. And after that, we are going to learn the wave and wave energy converter, wave structure interaction. Today's lecture, we are going to get two important concepts. One is added mass, another is radiation damping. So with these two concepts in mind, the wave energy converter will become a vibration problem. Okay, so in addition to that vibration mass spring damping, we also need to understand the excitation force. And so we are going to say today how the wave generate the excitation force. Okay, so basically we are going to learn wave structure interactions and WEC modeling. So WEC modeling, like yesterday we talked about Cummings equation, and today we learn what's the Cummings equation. Okay, so hopefully after today's lecture, in your mind, you can understand the WEC system or wave energy converter system, the modeling side. And tomorrow, we are going to learn the wave energy converter, the energy in the system, and the optimization for single degree freedom, 2 degree freedom system. Okay. And then after that, we are going to say alternating water column, and in your experiment, Professor Samet and Dr. Vijay, they design alternating water column. So then this is why we cover that part. So after that, we talk about PTO design and control. Okay, so today's lecture, there will be some equation here. And some equations you are going to learn two things. One is the physics behind the equation, right? Details, and if you understand the physics detail, you can figure out. Okay. Second thing, you need to understand the meaning of the added mass radiation damping and the impulse response. Okay. So let us start here. So first, potential flow, right? Okay. You already understand what's the potential flow, right? And in this potential flow, we don't consider viscosity, and we consider the flow is incompressible. Okay. So it's not irrotational, right? So let us say is you have a cylinder. Here you put in the water, right? And there's a flow speed u go across this cylinder. Okay, so we want to say what kind of force on that. Here, I directly give the potential flow, the velocity potential function, right? Here, and given this velocity potential function, you can find the velocity. This, you can say velocity, right? Here, with velocity doubled, right? And this part, the velocity will be 0, right? The velocity is a function of the radius, function of angle, right? You can write in that way, just from the potential flow function, you time derivative, right? You get this, okay. After you get that, we already learned the Bologna equation, right? Along the straight line like that, you look into Bologna equation, right? From Bologna equation, you can get a pressure. Pressure, and here U is at the infinity distance, and V is the velocity around the center, right? So P pressure is P infinity is at the infinity distance. What kind of pressure? Okay, now you have V velocity here. Now you have V sigma square, right? You plug that into equation, you get pressure like this one. That is the pressure along or in the potential field in any place, right? And now this figure gives you a sense about the pressure, right? And there are two lines. One is a streamline, black color, right? Another is potential equal potential line. So the potential this end is high and push the fluid to go this direction. Now, if you are given this pressure, we are ready to say what kind of force in the system. So what do you think is the force, and in x direction, in y direction? What's Fx? You can do the integration, but you look into symmetric. What do you first think? 0, right? So it's 0. And Fy, perpendicular to the fluid direction, usually we call the lift, right? That is 0 too, it's symmetric, right? You can do the integration, right? A small force integration projection, but quickly, if you look into that, wow, it's symmetric, 0, right? So now, and that is a center, there's a flow rate goes through that. Using the under the potential flow assumption, you don't have force on the system. Okay. So, and another thing is now we have 0 velocity, but your center is moving, right? You have tank, right? You may have carriage more this in the still water. Okay. So for this type of system, now what's look like? So first, the potential function, velocity potential function will be different, right? So velocity potential functions are different, and here you take the derivative, okay, and you will find this item, that's one disappear, right? And so VR equal U R square divided by small r square cosine theta, right? And V theta, you also get this expression. So now the Bologna equation will be different. And the Bologna equation, you say at infinity, this at infinity location, and the velocity is 0, right? And VR is this V already, right? Therefore, you plug into the system, you will find this VR square is just like a VR square, and this is V theta square, and this is, I need to shift that a little bit. You already say VR equal U and R capital R square small r cosine theta, right? This is U times R square divided small r square sine theta, right? And sine cosine theta square plus sine theta square is just U square, right? And after that, you say this expression will be different, and you can get the pressure equal infinity at infinity this position P infinity minus 1 over 2 rho U square. Okay, that is the pressure. So it's not this anymore. Okay, so now what the Fx and Fy? You just imagine that way. Now this pressure is not a function of theta and r, therefore look like a constant pressure. You have constant pressure inside, It doesn't matter how large the pressure is, the force, lift force, drag force will be 0, right? It is 0 again. So now, what if there's acceleration is not constant, right? And this U can be harmonic or can be acceleration. What does the system look like? Okay, so the potential function still takes this form. However, now the Bernoulli equation are different. Bernoulli equation here, there's an acceleration term, which is d phi dt. Okay, and d phi dt, you say here, theta is constant, right? And r is constant. Okay, you will have this term. Acceleration will show up here. You will do this one, you will say, okay, u is velocity, u dot is acceleration, right? You have acceleration term, you plug everything into this equation, you will find that the pressure now is function of theta and is also function of r on the surface of this cylinder. Okay, now if we need to calculate the lift and drag force, right? And here it shows a small segment, right? Is small segment that has surface length is dA, which dAx, okay, and A is the surface area, right? And surface area here, and if your weight is air, and S is ds is totally a small area, right? Will be r air time r d theta. Okay, now if you want to calculate the force and then the pressure force, you already know the pressure, right? Pressure time this area and you do the integration, right? And the integration you project into x direction, right? So as a result, you can do the integration, you find out, wow, now we have one force. The system, the force Fx is not 0 anymore. So how large is this force? Okay, so you say this force is proportional to the rho, which is water density. Okay, and pi r squared times this length. Okay, this is exactly how much the water mass of the cylinder. Okay, so you will have cylinder, right? They look like you have density of water, right? And times the volume. So that is we called added mass. So basically, you will have cylinder in the water, right? The cylinder is more constant, then there's no force using potential flow theory. If you have acceleration, then look like you have such kind of volume mass, you are going to do acceleration motion. So this is a concept of added mass. Okay, so and this is an important concept, right? You put the buoy in the water and then buoy will move. The water surrounding that buoy, there's acceleration, deceleration, and there will be mass effect. Okay, so mass is the force related with acceleration, right? You have mass, you more constant velocity like that, you wouldn't feel the force. Right, so you feel the force because of acceleration. So for this one, for this cylinder, it will be exactly the mass that of the water displaced by this cylinder. Okay, it doesn't matter the cylinder is copper or empty, what kind of shape inside. It's just volume of the water. Okay, with density rho. So in summary, okay, and the acceleration mass for this one, the physical meaning is the amount of the fluid exerted by the body, right? You move the body, the fluid will accelerate by the body. Okay, and in another sense, is the energy or kinetic energy of the flow surrounding the mass, right? So what that mean? And if you have particle motion, right, or mass motion, and the energy 1/m(v) square, right? So that is related with mass. Okay, so such kind of added mass will depend on the geometry of the body, also depend on the velocity direction. So just imagine that way. We said this is center, right? If you have center move this direction, the acceleration, the added mass will be different, right? So, and this mass, in this specific example, it has nothing to do with the frequency, right? You shake this thing at higher frequency, no frequency is same, but general case, added mass strongly depend on the frequency. At different frequency will be different. So this is one center case. Okay, how about a ball? Okay, here you can see a ball and it's half submerged, half in the air. And this figure, this line shows added mass, and this is the frequency. Okay, this normalized frequency omega square. Okay, you can get sense, right? And this added mass will be frequency dependent. At different frequencies, they are different. So later we are going to tell you what other two lines mean. Okay, so now I mentioned that it depends on different geometry. Here is the table, and you can say that table it shows different geometry and added mass effect, right? This is two-dimension one, and this is center shape. You move, right? And if center is not a round shape, right, it can be different shape, and this cross section matters, right? And you can have diamond shape, whatever like that. Okay, so you have flat plate, right? And the added mass depend on which direction it move, right? Then you can get this equation. So, okay, so this is two-dimension structure. How about three-dimension? Okay, like you have a ball in the water, right? And if you have a ball in the water, and similarly you use potential flow, right? And you have a velocity potential function, right? With the unsteady balloon equation, plug all these equation parameters here, you can calculate the added mass of the ball in the water. Okay, this added mass in the ball in the water is interesting, is different from center case. In the center, that is exactly of the water volume, same volume of the moving center. Here is half of the displaced mass of the fluid. You have this size of ball, you put it in the water, you have acceleration motion. So the added mass effect is half of the water displaced by the ball. Okay, so this give you another. This also give you sense that the shape matters. Okay, so now and you have ball, right? What if you have disc, right? Disc you move up and down, and you also see here, and this ball is half of the mass. Is this disc, right? The added mass compared with the one, this one is much larger, right? It's 2 times. Sure, you have square shape and you have different mass. Okay, so as I say, the center shape, if that is already give you sense about the added mass effect, right? So again, really depend on cross-section area. Okay, and this table, some of them you can get closed form solution, and like this. Some of them is more like numeric using coefficients for the correction. Okay, so this is the added mass concept. So such kind of added mass concept can be positively used. Okay, this figure shows a buoy in the water, right? And you see many cases when you have a small mass in the water, and then the vibration frequency is very, very high. Okay, and why is high? Okay, and in the water, the added mass, this is hydrostatic stiffness and physical mass. Hydrostatic stiffness is proportional to the cross-section area, right? So depending on water line, the surface area, and the mass is proportional to the diameter. Let us say you have ball, and stiffness proportional to the diameter square. The mass proportional with the diameter power 3, right? You have frequency square root divided k divided by m. Therefore, you have, let me say that way. So you just imagine that way. This is right, and where this stiffness is proportional to that diameter, right? If a ball in the water, right? Okay, and this mass is proportional to the power 3, right? As a result, as you say, 1 is r power 3, right? So that is proportional to that, right? So therefore, you have smaller diameter, you usually have high frequency, right? So high frequency, and actually Professor Farkau did some calculation. So assume you have half ball, it's a ball shape buoy you put in the water, half above the water, half below the water. You want to match the ocean wave excitation, such kind of ball need to be 52 meters. It's a huge ball, right? Normally, our buoy is small. When your buoy is small, the natural frequency will be higher. And then vibration is hard to create such kind of resonance, right? What you can do? So now you want to reduce the vibration. You want to reduce the vibration frequency. Vibration frequency, you reduce that, right? You reduce the stiffness, then you increase mass. Okay, now instead of using physical mass increase, we can add we can use added mass. So here I show a cup, right? And you put it in the water, and this cup, let us say this shape. Okay, now you have cup, and you just imagine that way. There's the mass. There are two parts. One is physical mass, another is added mass. So you have disk here. The disk will have added mass components inside. So you make this disk larger, then you didn't add physical mass, but look like you have large added mass to the system. Is this clear? Right? So, so this is one paper, right? Professor Samad, Vishlu, Saman, and I co-authored the idea here to use such kind of added mass concept to reduce the vibration natural frequency, right? We just add a plate here. We didn't add another physical mass. So therefore, this system stiffness wouldn't change, and we just add mass here. Okay. So I want to highlight some concept here, right? And how the added mass is generated is the acceleration of the water surrounding the body, right? And it depends on geometry, and it depends on direction, right? Here we use added mass then we reduce the natural frequency, right? So as a result, we can get more power. Okay. So wave energy converter, not all the wave energy converter are buoy, right? And this is another we call the alternating surge wave converter, right? We understand if your water is shallow and the horizontal direction, the particle motion is larger than the vertical, right? Therefore, if you have shallow water, alternating surge device is here. So for this alternating surge device, we also have added mass concept. And similarly, this added mass concept we called mass momentum. Mass momentum, right? And so itself is rotational system, right? This is mass momentum. So the physical meaning is if you flap more in the water, the flap will accelerate during the acceleration process, the more the water surrounding this mass. Such kind of water will have energy or there's a force to the flap. So, okay, how much is this one? So here, and the equation, let us say that when you have rotation disk here, right? And if you look into that, you say how large it is. Pretty large mass is half of the water surrounding this region, and you need to accelerate such kind of mass. And you need the flap shape, and to create such kind of oscillation, the flap density is significantly smaller than the water. Otherwise, it's sunk into the water, right? And typically, it's just 0.3 roughly, and 0.3 density is the water, right? So physical mass is very small compared with rotational mass. So just you have flap here again during the rotation, the physical mass momentum compared with the water, that this flap accelerate or decelerate is much smaller. So now when you check and the natural frequency, right, keep in mind in such kind of case your physical mass is small. Mostly mass is the water surrounding that. Okay, so this is added mass concept. Okay, and also different shape, right? You have different mass momentum, or this you can use some table to look into that. Okay, by the way, and one table there's something wrong, and this is I copy paste from the literature. Okay, so if you can find which term of the paper is this table number is wrong, we are going to give you credit for your course. Okay, you remember the evaluation, right? We have exam, we have report, right? And I'm going to give this handout to you. Okay, you figure out which of the items are wrong. Okay, let me know. Okay, so I just this copy from one paper and the summarize here. Oh, there's one typo. Okay, so you guys figure out. Okay, so and this is added mass momentum. So I said we are going to get two concepts cross, and added mass is one concept, right? So again, this is a very important concept in the wave energy converter. Sometimes the added mass is significantly larger than the physical mass. Okay, so when you work on the wave energy converter, you can take advantage of this added mass. Okay, the physical meaning is the water is moving, surrounding the buoy is moving. The buoy accelerate, and then the water accelerate, right? This water acceleration will have mass effect. Okay, so another concept we want to get across is radiation force. and radiation damping. Okay, what's the mean radiation? Okay, so like this one, you shoot a ball in the water, although that is water is still water, right? There's no wave, and you put a buoy there, the buoy move up and down. When the buoy move up and down, the buoy will generate a wave, right? The wave will propagate out. So that is called radiation, right? The buoy move up and down, the generate wave, the wave propagate out. This is radiation. Okay. So, and not only just now that shows heavy motion, that's one direction, and generally you put a buoy in the water, you have 60-degree freedom, right? And this is heavy motion, there's sway motion, surge motion, rolling motion, pitching motion, yaw motion, right? And let us say keep simple first, look into heavy motion only. And here it shows this buoy that doesn't need the ball shape, it's any arbitrary shape, right? You put it in the water, right? And now we consider vertical heavy motion only. Okay, so this come out. Okay, the heavy motion only, and this this can be 2 or 3 dimension flow. Okay, so in such kind of case, and what kind of motion you will have is this Newton's law, mass and time acceleration, there will be different components, right? And one is the excitation force, right? And if you have wave, there's a force, okay? And we are going to explain what's excitation force, okay? And there's a radiation force. Radiation force, as I mentioned, that they move up and down, and there's some radiation effect. Another is the hydrostatic force. Hydrostatic force and is what does that mean? Hydrostatic force. You put a buoy in the water, right, or basketball, whatever like that. You pull it down, right? The force increase, right? This is spring force, right? Hydrostatic spring force. Okay. Then another thing is PTO force. This PTO and this buoy can drive one generator. There can be linear actuator or ball screw rag pinion drive such kind of motion, right? So this PTO force. Now, let us say first take a look at the radiation force. Okay, before we talk about radiation force, there's an assumption, right? And like linear wave theory, you understand what we assume, right? Linear wave theory, we will assume wave amplitude compared with wavelength is much small. And another thing is we look into the water depths and wave amplitude, right? And wave amplitude is smaller than the water depth, than the linear wave theory hold. And for this one, we also have some assumption like that. Okay, we assume the body dimension, like say here, is A, right? And the wavelength is lambda, K is the wave number. Okay, the wave amplitude is A. So the assumption is, okay, and so this is a small wave theory. We already say that, okay. Let me say that way. No, let us explain to here. Okay, and the wave amplitude compared with the size of the dimension is small, right? And this is assumption. Another assumption is the dimension compared with your wavelength is small. Okay, this is why we call it point absorber. It's a 1 point compared with the wavelength. And the wavelength, as I mentioned, typically 50 or 150 meters in this range, and let us say 80 meters. And your buoy should be small, right? And what if your buoy is very large? If your buoy is same dimension as the wave, what happens? Just rock, right? The buoy will not move up and down, right? If a buoy is small compared with wavelength, then this move up and down is a point, right? It doesn't matter the wave come to this direction, comes to this direction is 1 point. Okay, so and we assume that the dimension is small and the amplitude, so compare with the geometry is small, right? You don't want this move into air too large. Okay, anyway, so under this assumption, and you can use linear wave theory, and we already say so linear wave theory, right? And you have phi d phi d square equals 0, the whole boundary condition, right? And wave theory is based on some simplified equation, simplified under the assumption of small wave theory. Okay, so similarly, when we talk about radiation force, and we use linear wave theory to understand that too. Again, the water is still, and then the buoy is moving up and down. Okay, so then you have radiation velocity potential in this field, right? And on the surface, and you will have, let us look into here, this bottom side. This z direction and velocity is 0, right? At z connect to h, in such kind of case, the velocity is 0, right? And this one, on the top of surface, you also have this boundary condition, right? And z equals 0, and also here on this surface, and you have the force perpendicular to this shape. That is what I mean. Okay, so under this assumption, you can calculate the total force act on the system, right? You have pressure, and n is normalized direction, right? You project to this surface, you integrate over this radiation force, right? Radiation force, and if you can find the velocity potential, you can get the radiation, get the pressure. Now you integrate that. Okay, for very simple shape, you can find the closed form solution. Okay, so instead of go through how to calculate that, I want to give you some physical insights. Okay, this is more important. So what's the physical insights? Okay, and here you assume this buoy or shape move at x amplitude, right? E j omega t or I omega t, that is a complex number, right? Unit number, okay. And cosine omega t plus I sine omega t, right? So now we assume that the radiation force take the complex number time e j omega t, right? That is x real amplitude. This fr is complex number. Complex number means there are phases into the system. That means the force may not be exactly in phase with the wave motion. So complex number, okay. And such kind of complex number, okay, and you can have real number, you have imaginary number put together like that. Okay, so the real number, imaginary number, what does it mean? Okay, at the instant time, the force, right? And there's real components and imaginary components. At time, this is complex number, that is total force, right? You take a real, okay. So instant force, and instant force here, if you have amplitude, real amplitude, and also there's some phase alpha here. So here, the real part corresponding cosine, right? Imaginary part corresponding cosine, sine. And this is cosine omega t plus alpha, and this real coefficients. Okay, so they have I here, and ej omega t corresponding sine here. You have phase, add them together. Okay, so that is force, instant force. Okay, for given the amplitude x. How about now we talk about force, and let us look into velocity. Okay, velocity, the displacement is given, right? Velocity and just time derivative, then you have amplitude, and here you take the real part, okay, and you become real is cosine derivative you become sine, right? You have phase here. Now you know the force, you know the velocity. Force times velocity, what's that? Power, right? Force times velocity is power. Okay, so this you plug this here, this time together, you will say instant power. This relationship take here, right? This sine 2 omega t and plus 2 alpha, this angle. Okay, here and this is sine square. Okay, so this instant power, you can say that way. In one period, what happened? And you take average in one period, this average out, right? And this is sine square. Then there's average here. You will find this instant power average will be proportional to x square and is proportional to omega square. Okay, so in one cycle, that means there's energy loss, right? And that's similar as the damper or energy harvester. What we say, okay, in one cycle, that's energy loss. This energy loss is proportional to amplitude square and proportional to omega square and proportional to the B, right? Now we call B as radiation damping, right? It has the same unit as viscous damping, right? So that means, just again, your ball or point of the ball move in the water, in a still water, right? And in such kind of case, you move in one cycle, the energy loss, right? This energy loss is proportional to x square and omega square, right? And this B itself is radiation damping here. So that is force. There are real part, imaginary part look like a damping. So another term here, this mass term, right? And this is A is added mass. We already learned the added mass concept just now, right? So added mass concept there, in one cycle, the mass store energy, return energy back. This is why in one cycle, that one, you don't have any energy. Okay, so why is added mass? You have physical mass, right? You have motion x dot square, and in time domain, you have m omega square x. Actually, you have negative sign. I didn't put a negative here. Okay, so this is, you compare with this, okay, a omega square x, right? This is m, this is a omega square x, that is m omega square x, right? You'll find A, they have the unit of the mass, right? And B have the unit damping. Now you understand, when the buoy move in a still water, what kind of effect? Two term, added mass, right? The water surrounding the buoy is moving, right? You have acceleration effect, and that's the mass. Another is energy loss. Okay, so we call it radiation damping. Okay, so that is in frequency domain, right? In time domain, you can also say, okay, A time the acceleration, B time velocity, right? This is force, right? One is mass term, another is damping term. Okay, there's some, I will come back to this again. I say this equation just for you to understand. But this equation, we shouldn't write in that way. Why? I mentioned to you, added mass can be frequency dependent, right? I put here, there, you say, A, it doesn't need to be a constant. So you say, oh, what kind of number I put there? Right? Similarly, you can understand B may be frequency dependent too, right? You put the number in the time domain, what kind of number I put there, right? For this one, it doesn't matter. Anything, this is frequency dependent, right? So for this one, is okay, and strictly speaking, it's fine. For this one, this is just for you to understand physically, right? And mathematically, it's not right because A is frequency dependent, B is also frequency dependent. It's hard to mix the time domain and frequency domain like that. However, this gives you good understanding, right? So the radiation force, there are two parts. One part is proportional to the acceleration, and this A. Another is proportional to the velocity, and this B. Okay, this is how the water and the buoy interact, right? I say the water, I didn't say the wave, because now it's still water, right? You generate wave. Okay, so I have one question here. We say the energy loss. Radiation damping is really damping or not? So you generate the wave propagate, and wave leave this buoy, but wave is still in the water, right? This energy propagate from one body to another body, right? It didn't leave this world, right? It's still there. We say the energy loss from your buoy, but such kind of energy is still in the water, right? So, okay, and such kind of thing is not the energy. Let us say radiation damping is the energy loss from the buoy, but this is not energy loss in the real world. The energy propagate from your buoy to other system. Okay, this is radiation damping. Okay, for your buoy is damping, but for overall world, the energy is still there. Okay, so radiation damping and added mass are related with each other. They are not independent, right? Here, under certain condition, so this can be calculated, okay? And also radiation damping is not negative, okay? And the added mass radiation damping, and if you know the radiation damping was frequency dependent, right? And you can calculate the added mass. If you know added mass here, you can calculate the radiation damping. Again, radiation damping is energy loss from the buoy, but not energy loss from the world. When I say this way, what you want to do. So I have a buoy here. The buoy generates energy, right? It's lost from this one. If I have another buoy here, it's gain, right? Therefore, if you put the buoy in an array, what happens? You put a buoy in an array. For example, I have this buoy, I have another buoy, right? And this buoy moves, right? If I put the positions right location, then this energy loss will be energy gain here. Therefore, I can have two buoys in the water, and the total energy we generated is more than one buoy times 2. Make sense? Because this become wave maker to this one, the energy loss we get more, right? This one 2, so here 1 plus 1 is more than 2. Make sense? Right? Because energy didn't loss, energy just not move from one body to another body. Okay, so that is one paper published by Dick Yue. Professor Dick Yue is expert in the whale, and he is in the ocean engineering program. Previously was department at MIT. He published the paper with his student. Okay, so basically you put a buoy in a ray in the water, right? And if you place the buoy distance right, and the wave angle and the wave number is right, then you can get much more energy than individual buoy, right? And in his paper, he can get 3 times more power, right? Just imagine that with 3 times more power, what I mean is from here, you put, let us say, 100 buoy, and the total energy you can generate is 100, it's not 100 times 1 buoy, it can be 300 times 1 buoy. Okay, so meanwhile, also you understand that is sensitive to the location geometry, right? How close this dimension, that how in which kind of distance a wave will come in. Okay, so this radiation force. Okay, now I get 2 concepts crossed. One is added mass, another radiation damping, right? And so this now we are going to talk. We also say how to take advantage of the added mass, right? We also can take advantage of radiation damping. So most of the time, radiation damping is, we think, oh, damping energy loss is bad, but we can take advantage of that. Okay. So another thing is the excitation force. Okay, so excitation force, what does that mean? Okay, so you just imagine that way you have buoy here, your buoy fixed, you have wave come in, right? You have wave that we call the incident wave, right? You have wave come in, and then some wave will get a deflection, right? This happen, right? For example, you have another wave. After that, the wave becomes smaller, right? Something go, right? And if this point absorber is small enough, and this wave pass through, probably wouldn't decrease too much, right? Anyway, this is incident wave and diffraction wave. So, and this wave will have force to the system. Now again, your buoy is fixed, right? The buoy is not moving, the wave is moving, and introduce a force. We call this excitation force. Okay. How to understand this excitation force? As I mentioned, that incident wave come in, and then if we have velocity potential is 5I incident wave, right? And then you have diffraction wave leave the system, you have 5D, another velocity potential function. Okay, so you overall this system you can have similar and boundary condition on the surface, chaotic boundary condition, and also geometry, bottom side is velocity, the boundary condition, right? On the surface, right? You can solve the potential flow function. You can calculate the total force, right? This force contribution and the excitation force contribution, there are 2 parts, right? One is incident wave, another diffraction wave. In certain situation, and this contribution can be small, and what kind of condition? Okay, if this buoy, right, under this water, or this body is relatively small compared with wavelength. Most of the time it's this case, right? Wavelength easily can be 80 meters, but your buoy probably 0.8 meters, right? Or 2 meters. compared with that is small. As a result, the differential term induced force, this type of thing can be ignored. You just think, okay, this will come in, this is how much is excitation, right? Then you ignore the differential term. Okay, so, and that is the force we can calculate relatively easier. Okay, so let us say that way. Wave amplitude again is x e omega t, right? And there's the cosine plus I sine term, right? Real part, imaginary part. Then you have excitation force, and excitation force here, and it is proportional to the wave amplitude, right? We normalize that. We can say this is the excitation force amplitude normalized by the wave amplitude. Okay, so in such kind of wave, and if you have symmetric, exosymmetric body, right, and in deep water, okay, and such kind of excitation force and radiation damping are related. You can calculate, right? For example, here we know how previously we already say radiation damping term, right? If radiation you have buoy, mostly symmetric, right, in the deep water, and you can calculate the gamma that's normalized excitation force. Again, and the radiation damping and added mass is related. And here, excitation force and radiation damping is also related. Okay. So I mentioned that this figure I'm going to come back to again. This is normalized frequency. Okay. And then this line is the frequency dependent added mass, right? And added mass and radiation damping, so let us say that way. Added mass and radiation damping are related. So this is radiation damping term. Okay, and here you show the excitation force, right? And you can calculate using the radiation damping here is like that. So these three are frequency dependent, right? For simple shape, and you can find a closed form solution. For more complex shape, use the numeric method. Actually, what you solved is potential flow theory, right? Using potential flow, you can get these three terms, and added mass, radiation damping, excitation force are frequency dependent. Look at this figure again. I want to point out something. So you can say added mass here, right? It wouldn't change too much along this frequency. Radiation damping can change very quickly, and from very large number to something close to zero, right? Radiation damping change with the frequency quickly. And the excitation force also is a function of frequency. If you want to design something, what you want? You want to have excitation force maximum at that frequency, right? You want to have some radiation damping small, right? So all this design really depends on shape. This ball shape, you say here, you want to have at this part the force, excitation force large at this frequency, right? Radiation damping is reasonably small. Okay. So next lecture we are going to talk about the excitation force and radiation damping, how we apply this to the vibration system, harvest energy, talk about the power optimization. So here we give you sense about excitation force, radiation damping, and added mass. Okay. So, okay. Hopefully, you guys get the point. Added mass, radiation damping, and excitation force. Okay. So, not confusing enough. Next is the 1.5 hour. I will confuse you guys more.